Thank you for the introduction, and thank you to the organizers for giving me the chance to speak here, and thank you to the IPAM staff for making this event run so smoothly. So today I'll be talking about joint work with Jesse Peterson and Ishan. Jesse was my postdoc mentor when I was a postdoc at Vanderbilt, and Ishan is his student. Ishan is on the job market this year. So in the past, when I've talked about this paper, I've focused on group properties and the definition of a properly proximal group and a sketch of our proof that proper proximalities measure equivalence invariant. But today, since this workshop is called Actions of Tensor Categories on C-star algebras, I'm going to focus on the parts of the paper that maybe some people here working in tensor categories or C-star algebras might be able to generalize to tensor categories acting on C-star algebras. So to start with, I'm just going to draw a diagram that gives you some relationships between, gives you some equivalences between groups. Okay, so throughout this talk, gamma and lambda will be countable groups. So if we're comparing two countable groups, there are some questions we can ask. We can ask, are they, let me get some things out of the way here in my Zoom window. We can ask, are they isomorphic? Or maybe they're not isomorphic, but maybe they're commensurable. So what does it mean for gamma and lambda to be commensurable? It means that there exists h in gamma, k in lambda that are both finite index. And we have an isomorphism between h and k. Okay, so at this point, maybe they're not commensurable. We can go in two different directions. So remember in Kristen's opening talk, she said that von Neumann algebras are more measure theoretic and C-star algebras are more topological. These are the two directions that we can go from here. So I'll write down on the one hand, the definition of measure equivalence. And then on the other hand, the definition of quasi-isometric. So what does it mean for two groups to be measure equivalent? It's a definition due to Gromov. It means that there exists an infinite measure space with measurable measure preserving actions of gamma and lambda such that gamma and lambda each admit a finite measure fundamental domain. And what that means is there exists x and y finite measure such that I can decompose my infinite measure space using translates of x and y by gamma and lambda respectively. Okay, and then on the other hand, I'll write down the definition of quasi-isometry. This is the definition that Gromov proved to be equivalent to the original definition of quasi-isometry. Gamma and lambda are quasi-isometric if there exists a locally compact metric space M and an action by homeomorphisms on M, commuting for gamma and lambda, such that the actions of gamma and lambda on M are properly discontinuous and each have a compact fundamental domain. So I'm going to be talking for the rest of the talk about the left-hand side, specifically about this new notion from our paper, this new notion of von Neumann equivalence, where we replace the infinite measure space with a semi-finite von Neumann algebra. So if we're going to replace this infinite measure space with a semi-finite von Neumann algebra, then what will be the fundamental domain? So look back at measure equivalence. And notice that on the level of function spaces, this characteristic function, where x is the fundamental domain, gives a projection in here, this von Neumann algebra, such that the collection of characteristic functions where we look at the gamma translates of the fundamental domain forms a partition of unity. So what does it mean to form partition of unity? It means this in the strong operator topology. So let's try and generalize this from the commutative setting to the non-commutative setting. I'll make this definition. This is the definition we formulate in our paper. So if M is a von Neumann algebra, then we say that a fundamental domain for the action of gamma on M is a projection P in M such that the gamma translates form a partition of unity. Okay. In the strong operator topology. So now we're ready to formulate our definition of what it means for two groups to be von Neumann equivalent. We say that two groups are von Neumann equivalent if there exists a semi-finite von Neumann algebra with semi-finite faithful normal trace and trace preserving actions of gamma and lambda that commute such that these actions each admit a finite trace fundamental domain. individually. They could be the same. So now let me give you some examples. So you can see that first of all, measure equivalence, if two groups are measure equivalent, then they are von Neumann equivalent. How do you see this? Take as your semi-finite von Neumann algebra L infinity of your infinite measure space. Okay. Second, Wstar equivalence, which I'll add to this chart, implies von Neumann equivalence. So Wstar equivalence, that just means that, let's see where I want to fit this in here. Wstar equivalence just means that the groups have isomorphic von Neumann algebras. And something related, which I'll come back to later, assume that gamma and lambda are ICC, so the von Neumann algebras are 2-1 factors. Then we talk about virtual Wstar equivalence. And this means that each factor is stably isomorphic to a finite index subfactor of the other. Okay, so we have this implication, which I'll talk about right now. Wstar equivalence implies von Neumann equivalence. And this one, of course. And we show in our paper this one. And there are some non-implications in this chart of group equivalences, which I'll add later. But first, let's get through the examples. So I need to give you trace preserving commuting actions and a finite trace fundamental domain. So what will these be for, let's say we have an isomorphism of von Neumann algebras. Then we'll end up taking as our semi-finite von Neumann algebra that'll give the von Neumann coupling. This von Neumann algebra. And then for the trace preserving commuting actions, lambda will act on M by these operators. Okay, so that's the right regular representation. And gamma will act on M by these operators. Okay. And then what's the fundamental domain? Rank 1 projection onto the subspace, this subspace for both the gamma and lambda actions. Okay, and so far these two examples involve type 1 semi-finite von Neumann algebras. So what about one where M is type 2? How about Suppose that we have these trace preserving actions to start with. Gamma acts on a finite von Neumann algebra, and lambda acts on another finite von Neumann algebra. And suppose we have trace preserving isomorphism from this crossed product to this one, such that the isomorphism takes M1 to M2. Then this extends to an isomorphism of basic constructions. Taking one conditional expectation to the other. And then what are the trace preserving commuting actions and what is the fundamental domain? So we have gamma acting on our, and what is the semi-finite von Neumann algebra giving the coupling? Let this be this cursive M. So that's our semi-finite von Neumann algebra in the von Neumann equivalence, playing the role of the infinite measure space. And gamma acts on this cursive M by these operators. And it pointwise fixes this. And lambda acts on M by these operators. Which commute with the action of gamma. And then for the fundamental domain, we take EM1. And I can talk more about these examples in detail. I'll have to go immediately after this talk ends, but later in the week, I'll take more questions during one of our breakout room discussion sections. Okay, so these are the examples we have, but I haven't told you anything about the motivation for formulating this definition of von Neumann equivalence. Okay, so why did we do this? I'll write down a theorem, the theorem that started everything. This is a theorem due to Boutonnet, Johanna, and Peterson. In 2018. I won't define all the terms in this theorem, but so if gamma is properly proximal, I'll tell you what that means in a minute. And lambda is an arbitrary countable group. And we have an action of lambda on this measure space that's compact, free, ergodic, and an action of gamma on this measure space that is just arbitrary, but still free and ergodic. Then Boutonnet, Johanna, and Peterson showed that for this class of groups. If you know that these von Neumann algebras are isomorphic, then you know that these actions are orbit equivalent. So Utane, Joanna, and Peterson sought to generalize results of Ozawa and Popa, Chifan and Sinclair, Popa and Voss. These are structural results on von Neumann algebras built from groups that are, I'll just say for now, like SL2Z. They were trying to generalize these structural results to von Neumann algebras built from groups that are like SL3Z. And it turns out that the class of groups for which they were able to prove these results is a very wide class of groups that includes both SL2Z and SL3Z, called properly proximal. So now what does it mean for a group to be properly proximal? Just briefly, this isn't the definition that we use in our paper. Not so much. So we say that a group is properly proximal if there does not exist a left invariant state on this C-star algebra. Okay. Here, rho gamma is the action induced by right translation. So this C-star algebra, these are the fixed by right translation. And you should compare this definition to the definition of interamenable. And a group is interamenable if there exists a conjugation invariant state on here. Okay, so without really getting into group properties at all, you can see from these definitions I wrote down that properly proximal implies not interamenable, and interamenable implies not properly proximal. So questions from Utane, Joanna, and Peterson's paper. Okay. One is proper proximality a measure equivalence invariant? Okay. And another is, looking at these two definitions, does there exist a group that is neither properly proximal nor interamenable? So in our paper, we're able to answer these questions, and these questions led us to formulate what it means for groups to be von Neumann equivalent. So now I'll write down the results from our paper. We show that proper proximality is a measure equivalence invariant, Wstar equivalence invariant, and von Neumann equivalence invariant. And as a corollary, we are able to say yes to this, thanks to an example of Capras that is in a paper of Duchesne, Tucker, Drobe, and Weselek in 2018. Okay, so now let's go back to this chart and fill in some non-implications, and then I'll discuss in more detail how we showed that von Neumann equivalence is indeed an equivalence relation. So how we showed that it's transitive. Okay, so what are some non-implications in here? Zoom out. Okay. So here's the entire chart. And we have a non-implication going from measure equivalence to Wstar equivalence first. Okay, so this is no, and this is due to Popa and Zlitchenko in 2018. And we also have a non-equivalence from, oops, that one's Chifon and Joanna in 2018. And we also have a non-equivalence going from a non-implication going from measure equivalence to virtual star equivalence. And this one is and this was actually 11 here. Okay, so that gives us also these non-implications involving von Neumann equivalence. Okay, so a big question we have is, do there exist gamma and lambda such that gamma and lambda are von Neumann equivalent, but they're not measure equivalent? Okay. We're not sure. All right, so in the remaining time, I'll talk about our proof that this is indeed an equivalence relation, which boils down to proving that von Neumann equivalence is transitive. Okay, so first we start with, and I'm writing this down in the hopes, just very quickly in the last few minutes, in the hopes that maybe someone here can do what we've done for these two countable groups acting on a semi-finite von Neumann algebra and think about tensor categories acting on a C-star algebra, generalizing this, because we don't have anything. Oops, there's a bit of a lag in my tablet. We don't have anything down here for C-star algebras. Okay, like we do with von Neumann equivalence over there. Okay, so suppose we have von Neumann couplings between countable groups gamma and lambda, and lambda and call it sigma. And these couplings have fundamental domains, finite fundamental domains, like this. Then we show that just using general theory of projections in semi-finite von Neumann algebras. Okay, so what is this? This is the gamma, lambda, and sigma act naturally on this new von Neumann algebra here, and lambda acts diagonally on both m and n. So these are the lambda fixed points here. Okay, so we show that this has a faithful semi-finite normal trace, and it's given by So we're using the fundamental domains we had to come up with this trace and to come up with our new fundamental domains for this new coupling. Here are the fundamental domains, and I'll stop after this. For the action of gamma, the fundamental domain looks like this. And then for the action of, so that's for gamma, and then for the action of sigma, fundamental domain looks like this. And I'll go ahead and stop there. Thank you.